All right. All right. First idea. To understand this chapter, you have to look at what is proton number. Proton number will be number of protons, right, in the nucleus of an atom. And nuclear number will be the total number of protons and neutrons in the nucleus of an atom. So proton number, number of protons in the nucleus of an atom. Nuclear number will be total number of protons and neutrons in the nucleus. Okay, we're in chapter 6. Okay, I hope you all can recall back what are isotopes that you learned in chemistry. Same proton number, but different number of neutrons. All right. So isotopes are from the same element, just that their number of neutrons will be different. Okay, so they'll have the same chemical properties. Physical property by mass will be different. Okay, now radioactive substance. Okay, why they are so popular? Because they have a lot of isotopes, radioactive elements or substance. So once they have their isotopes, they are called radioisotopes, right? For example, like uranium 235, 236, and so on. Okay. Radioactive element. Why radioactive elements are very popular? Radioactive elements naturally will have an unstable nucleus, right? Radioactive elements will have an unstable nucleus, huh? Okay. Let's do a simple recap. A nucleus contains protons and neutrons. Which of these particles experience an electrostatic force? Definitely protons, because it is positively charged. All right. And then we have gold, 79 protons, 118 neutrons. So if there's 118 neutrons and 79 protons, total nuclear number will be 197. 79 plus 118, you get 197. So it will be proton number and nucleon number. So if you're going to write this symbol, you have to use your method of writing. So our, all right, proton number 79, nucleon number will be 197. All right, next. An isotope of nitrogen can be represented by, it's given here, 15.7. How many of the following particles does it have? Proton, 7. You can say 7. Neutron, 15 minus 7, 8. All right. Electron, if it's an atom and neutral, number of proton equal number of electron. So 7. All right. Okay, done. Okay, basically, this is the first basic idea. Okay, now radioactive decay. All right. Let's see what happened. So radioactive elements will have an unstable nucleus. So radioactive elements will undergo radioactive decay. Okay, so if you look at it here, first you have an unstable nucleus. Why the nucleus unstable? Maybe huge nuclear number, or some even though small, like carbon-14, but still not stable. All right. So unstable nucleus will decay, mereput, decay on its own. When unstable nucleus decay, it will form radiations such as alpha, beta, and gamma, produce heat and will try to form a new nucleus which will be more stable. So whenever radioactive decay occur, it will be a spontaneous disintegration. Tiba-tiba berlaku. It can suddenly occur. You don't know when, but it will occur. Right? It will never be influenced by pressure, temperature, and chemicals at all. So you can't tell me, oh, I pour acid and it decay. No way. It has its own time, half-life system, it will decay on its own. All right. So whenever you look at this idea, whenever you have an unstable nucleus, it's decay on its own. It is a radioactive element. All right. If it's an isotope, you call radioisotope. So an element with stable nucleus, we just call atom, normal element. Once the nucleus becomes unstable and decay on its own spontaneously, it will be called radioactive element. And if it happened to be an isotope, we call it radioisotope. Okay, next here, radioactive decay. All the radioactive decay, there will be formation of new element, and of course they will release alpha, beta, and gamma, everything. All right, they have radiation and they can form new element. So for example, iodine 131, once it decay by releasing 1 beta, it's forming xenon. All right, okay. So proton number increased by 1 and nucleon number, all right, It's changing. It's not a complete one. I'll show you later. Okay, next. Study characteristics of radiation. So now you saw, just now you saw that whenever elements decay, they try to form the spontaneous process dengan sendiri tiba-tiba suddenly will occur. They try to form a new stable nucleus. Sometimes it's one step, one sequence. So it can be a multiple sequence, one after one, all right, until the final stable one is formed. Okay, whenever this process occur, every radioactive element during fission, fusion, and spontaneous disintegration or decay, they will release radiations, alpha, beta, gamma. Some will release all three, some will release only two, some might release only one. Okay. Commonly released is gamma ray. Almost every radioactive decay will be releasing gamma ray. All right. Some release beta and gamma, some alpha and gamma, some alpha, beta, and gamma. All three will be released together. Okay, so what's happening now? See, symbol of helium. Helium is the nucleus of alpha is the nucleus of helium. So 4-2, it's positive 2 charged. All right. What is alpha? Alpha is the nucleus of helium. So whenever a decay takes place, whenever nucleus of an unstable atom decay, one of the pecahan, serpihan, fraction will be alpha. All right. So it's nucleus of helium. Then you have beta. Beta will be electrons, fast-moving electrons. All right. This electron actually came from the nucleus. The question comes now. Hey, nucleus got electron? Yes. Yeah. When these elements were formed, as you all know, in the nucleus, we have protons and neutrons, right? What is the nature of neutron? Actually, when electrons were forced to be embedded to a proton, you get what we call as neutrons. So millions and millions of years ago, when these atoms, these elements were formed, electrons from outermost shell were forced to be embedded to protons, and you get what we call subatomic particle of neutrons, right? So the high-speed neutron that comes, there's a high-speed electron that comes from the nucleus. We call it as electrons, which is beta, all right? And finally, gamma ray, it's a ray, it's not particle actually, it's a ray. Gamma ray is actually an electromagnetic wave. It's actually an electromagnetic wave. So, nature of radiations, alpha particle, nucleus of helium, alpha, all right, nucleus of helium, alpha, positive 2, beta, high-speed electron from the nucleus, very high energy. Common electrons are orbiting the nucleus, but beta, high-speed electron from the nucleus, and gamma ray, it's actually an electromagnetic wave, which is coming out from the nucleus, right? Okay, so charge, you see already, positive 2, negative, and this is neutral. Alpha will be the largest because it is made of 2 protons and 2 neutrons, a bit heavy. And then beta, very small, tiny, high-speed electron. And gamma ray got no mass because this is a wave, an electromagnetic wave. It won't have any form of mass, right? Next. Look at speed. Alpha can travel up to 10% speed of light. Beta can go 90%. Gamma is wave. It is an electromagnetic speed of light. The ionization strength, you should know that since alpha, all right, it's made of 2 protons and positively charged 2 protons, 2 neutrons, and it's positive, so it will have a very strong ionization effect, strong, right? Beta, medium, not very strong, but sometimes depend on intensity. So this is very subjective. If let's say that element, radioactive element, can emit very high amount of electrons, then ionization is very strong, right? Mainly it's medium. Gamma ray is neutral, so weakest or none, right? Other. Okay. Penetrating power, ionization, penetrating power, alpha, as you know, it's actually a fraction of an atom. It's the nucleus of an atom of helium. So it will have the lowest penetrating power. It can be easily blocked by even a paper. All right. Can be blocked by your baju. So penetrating power of alpha is the weakest. All right. It can't even penetrate simple cardboard, right? Paper. Beta can penetrate through tissues, paper, all right. It can be blocked by, all right, aluminium plate. Aluminium plate, minimum a few thickness. So penetrating power of beta is a bit strong, depending to the strength of emission. Gamma ray strongest. All right, it can penetrate through your body easily. Come on, it can penetrate through any wall. All right, so penetration power of gamma ray is the strongest. All these are not given in the textbook, so I'm taking back all from your Form 3 work. All right. Next, if you look at it here, alpha positively charged, right? Since alpha is positively charged, alpha will have deflection in electric field, slightly deflected. Beta negatively charged, a bit more. Gamma ray is neutral, it's a wave. You can't get all that, all right? Magnetic field also can, all right? Then here great, here none. Range in the air. Alpha, once it is released from, let's say this is your radioactive source, alpha, releasing alpha, it's coming out from the nucleus, right? You only move to a range of a few centimeters, maybe 5 cm or maybe 10 cm, based on the substance, based on the radioactive element, and based on the intensity. Berapa kekuatan, keamatan dia pancarkan, based on that. Beta can go up to a few meters. Gamma is the best, it can move up to kilometers, all right? Highest range, and you know it's moving at speed of light. What is speed of light? 3 times 10 to the power of 8 meter per second. So this is extremely strong, yeah? Okay, next. What are the devices we can use to detect radiation? Number one is cloud chamber. Cloud chamber. So you put your radioactive source here. You see from on top here. We don't have all this in the school. You can see the track, how it look like. All right, okay. So it's not really in the syllabus. I'm just showing you all only. So radioactive source is here. So with the help of the alcohol vapor and the very low temperature, you can see the track when you see from on top here. All right. So these are the parts of the cloud chamber. You can read this. If you don't know, later you can ask me again. Okay. But how the tracks look like? When you see from the upper part, right, you realize, all right, okay. Kalau you tengok untuk alpha, all right, you see a very thick tracks. All right. For alpha, you see a very thick tracks, right? Alpha, you can see a very thick tracks, all right? Very thick one. The lines here. So this is the source. The source of radioactive element is here. The source is here. All right. It comes out from the source. Very thick tracks. Okay. But if you see for beta, you get some wavy tracks which is not very thick. All right. It's a bit thin. All right. It's a bit thin. See for beta, you see like that, something like that. Not so thick. Right. Because ionization strength of alpha is the strongest, and it's actually nucleus of helium made of 2 proton and 2 neutrons. So it's a bit heavy. It's like moving big and knocking all the air particles. But here beta is pretty small, and gamma ray nothing you can see. All right, we can see some wavy tracks, so-called tracks. All right, so for alpha, if you see from the surface of the cloud chamber on top, you can see like this. For beta like this and gamma ray like this. Okay, I just repeat. See what happened actually inside the cloud chamber is that you have to place your radioactive element here, here, and you have to see from on top. From on top, you see from here, you can see the tracks. Okay, this whole area will form something like a artificial cloud inside here with the substance, with the solid carbon dioxide, with the vaporization here and the low temperature. See something like a cloud here, and once you put the radioactive element from on top, you can see like lines in the cloud. The lines in the clouds are the tracks. Huh? We're done with that cloud chamber. The next device will be the Geiger-Müller. So this is pretty accurate. This is the aluminum cylinder. You see the reading here. From the reading, you know what is the radiation strength. Okay. These are the other examples of Geiger-Müller. All right. Okay. Then you see how it works. So your radioactive source will emit alpha, beta, gamma. Alpha will be positively charged, and it can penetrate through the very thin mica window, and it has to be very close. So the charge here will be discharged, and it will actually allow current to flow. The rate meter will amplify, and based on the current flow, you can hear sound here. Okay, there's a sound like a trrr, trrr, like that. Okay, There's a sound system here. So based on that, we know what is the amount of radiation we are detecting. It's all not in the textbook anymore. Okay. So Geiger-Müller, accurate, portable, easy to carry. We know how to detect radiation. We'll know what's the value based on count per second or count per minute. So this system will be vibrating. The vibration here, the count per second or per minute, from that we'll know it. Okay. What's the radiation we're detecting? And the earlier one is the cloud chamber. Okay, the next one is this the one, the photographic film. Most of the people working, doctors, people working in nuclear industry, radiologists, all be wearing this badge, right? This badge nowadays is actually digital. They can just take this and slot to a computer system and tell them what is the amount of radiation they're exposed to. Those days are very manual. They see the color changes. Based on the color, once they're exposed to radiation, the color will change. Based on the color change, they know what is the amount of exposure they've gone through. So I gave you Geiger-Müller, and then I gave you cloud chamber. So all this can be used to detect radiation around Earth. Right? So next, spark counter, another simple device. They will place the device in the lab normally, or in the place of storage. So this device, once it's actually there's a radioactive source, will start to produce a lot of sound because of ionization, alpha, beta. So due to the sound, we'll know, oh, this area got some radiation, might be very strong also. These are spark counters, right? Okay. Now, other simple type of radiation detectors, we carry a dosimeter. You can buy in Shopee also. All right. This can show you the amount of radiation around us. So people working in police or in the rescue team or hospitals, they might carry this also. All right. Okay. Then if you are moving around any jungle area or any mining area, they carry a gamma spectroscopy. This is what industries will keep. They'll show the radiation level. It's called gamma spectroscopy. Right? It can identify isotopes also. Okay, next. Finish with that. All right. Okay, now what are we going to do? We're going to look at, now we start with the syllabus. Okay. So radioactive decay, we have alpha decay. First, we start with alpha decay. How does alpha decay works? You see here carefully. All right. Let's say you have a radioactive element with 100 nucleon number and 50 proton number. When it decay, all right, on its own, for example, katakan, this element will form a new element because it's releasing one alpha. When one alpha comes out from the nucleus, we write like this. Alpha is nucleus of helium. So the nucleon number will decrease by 4 because helium will have 2 proton and 2 neutrons. The total nucleon number is 4. The proton number will decrease by 2. So you get 48. And you can rewrite energy at the site. All right. So every time there's an alpha decay, this is alpha. All right. Initial element and the final element. So initial radioisotope, nucleon number 100, final 96, initial 50, now 48. And it has released 1 alpha. If let's say 2 alpha, all right, now I'm going to delete this. If 2 alpha, we rewrite like this, see here, right? So initial element, nucleon number 100, proton number 50, going through a spontaneous disintegration to form a new element of Q. But it has released 2 alpha, and a lot of energy. The energy might be in the form of gamma ray, all right? So what is the new nucleon number? 2 times 4, 8. So 100 minus 8, you get 92. 2 times 2, 4. So 50 minus 4, 46 out. This is how you rewrite. All right. So alpha decay, make sure you do your mathematics properly. So 100 equals to x plus 2 times 4. So x will be what? 92. Right. Then here 50 equals to y plus 4. So y was 46. That's how we count. Okay. Done with alpha decay. So every element that going through a spontaneous decay, dengan sendiri they'll release the alpha. Next. Beta decay. Listen carefully. When you look at the nucleus of an element, okay, let's say it's element X again. Now, this time don't element X lah, okay, some other element. Okay, sorry. Okay, let's say the element is now element P. All right. It has, let's say, nucleon number 20, proton number 8. All right. When it's decay, it's forming a new element M. All right. By releasing one beta. Beta, this is the symbol, right? Nucleon number 0, proton number -1. Ni cara tulis. All right. And this is the energy. So, whenever beta decay occur, nucleon number remain the same. Proton number will increase by 1. So 9 plus -1, you get 8. So before and after must be balanced. 20 plus 0, you get 20. So this is how we look at beta decay. Beta decay goes like this. All right. So beta decay goes like this. Right. So every time before and after, you make sure you balance the nuclear number and proton number. So beta decay. All right. I give you another example. Carbon 6. All right. Nucleon number katakan 13, 14. Okay, carbon 6. So 6 proton, 8 neutron. All right. It goes through a decay by releasing, so we call this carbon 14 actually. Okay, we call this carbon 14. So it's releasing one beta. This is beta, and of course, a lot of energy. So what we learn, nucleon number should be the same. Proton number must, because release 1 increased by 1, so you get 7. It's actually nitrogen. So whenever carbon 14 decays spontaneously, it is forming a new element, nitrogen. All right, this is how you get it. Okay. So any example here, right? And next we go for gamma decay plant. Gamma. Okay. Let's say you have an element, right? This is element R. Initially, nuclear number was 40, proton number 20. After emitting only gamma ray, all right, which is the form of energy, gamma ray, the new elements still remain the same. Then what is the difference before and after? This one with high energy and the other one with low energy, that's all. When you calculate the energy, there's a way to calculate the spectrophotometer. You'll see this one with high, this one low, that's all. Gamma decay, when gamma decay occur, the level of energy after it has gone through a decay of emitting gamma, they're a bit low, it's not a bit high, that's all. Tinggi dan rendah. Tenaga dia tinggi. Alright, that's all. Tenaga tinggi, tenaga rendah, that's all. Alright. So gamma is a bit easy. So gamma got nothing much to minus plus all. Okay. Let's look at other examples. So uranium to thorium. So uranium, right? It's 234. Alright. And you get 92. Alright. Then, so this is uranium 238, uranium 230. So these are isotopes. See, this is thorium 234, thorium 230 isotopes, right? So uranium 234 undergoes a decay series to form thorium. And this thorium shows the nucleon number is 230 and proton number is 90. So when I see here, I realize, oh, nucleon number decreasing by 4, proton number decreasing by 2, confirm this is helium, which is alpha and energy. All right. So number 1, this is number 1, first decay series. Second, number 2, second series. Third one, and the fourth one. Let's do the last 5 and 6. All right. So how does it work? Okay, to look at here, thorium 5 and 6. Okay. So there are 6 decay series. How I know? There's a number of arrows. Okay. So thorium 230, proton number 90, decay to form radium. All right. This is radon, radium. All right, this is 226. All right, and this 88. So if I see 230, so nuclear number decreased by 4, proton number decreased by 2, confirm another alpha. All right, and energy. And the last decay series is radium to radon. So radon is 222, proton number 86. So decay to form, sorry, radium, right? Sorry. Okay, radium 226, all right, and this 88, right? Okay, decay to form radon. And radon is 222, 86, guys. So what was emitted? 4 and 2, again helium, all right, which is alpha. So this is the energy. So if I count here, how many times alpha was emitted? Alpha was emitted 1, 2, 3, 4 times. Beta, 2 times. Beta, this is beta. 2 times beta, all right, and 4 times alpha. This is how we identify decay series. This is how we actually write the equations, all right? Okay, next. We'll talk about half-life now.